So now definition. H Hilbert space, an orthonormal set in H is said to be complete if it is maximal of course with respect to the partial order induced by set inclusion. That means there is no other orthonormal set which contains this one and is strictly bigger than this. So that is the meaning of the set, saying it is maximal. In that case, a complete orthonormal set, sometimes we write CON, is also called an orthonormal basis. It's another name for a complete orthonormal set. So proposition: every Hilbert space admits an orthonormal basis. So proof. So we do have orthonormal sets. In fact, if you have any x is not 0, then you have x by norm x is an orthonormal set. And then if you are given any linearly independent thing, the Gram-Schmidt process gives you an orthonormal set. So we have a lot of orthonormal sets. So the collection of all orthonormal sets is non-empty, and you put a partial order on the collection of all orthonormal sets, namely set inclusion. So E1 is less than or equal to E2 if E1 is contained in E2. So now you take any chain, then union is an upper bound. So you take a chain, that means any two elements of the thing, simply take the union, that's an orthonormal set, and therefore that will give you an upper bound. Implies there exists a maximal orthonormal set by Zorn's lemma. So it's a very simple application of Zorn's lemma, that every Hilbert space has a maximal orthonormal set or an orthonormal basis. Okay. So now we have a very important theorem. H Hilbert space and EI I in I an orthonormal set in H. Then the following are equivalent. One, the ON set is complete. Two, if x belongs to H, x orthogonal to EI for all I in I, this implies x equal to 0. 3, x is in H, then x equals sigma I in I, x EI, EI. We know how to define this sum. and if you take the sum, it has to be x. So then is equivalent to saying that the space is complete. 4, this is called so norm x in h, then norm x square is equal to sigma I in I mod x ei square. So this is called Parseval's identity. Okay, so proof 1 implies 2. So if x is not 0 but and x orthogonal to ei for all I in I, then you take ei I in I union x by norm x. So this is again a unit vector and it's orthogonal to all of these. So this is an orthonormal set, strictly bigger than ei I in I, and that's a contradiction because we know that it is complete and therefore this is maximal. Okay, so you cannot have something bigger. 2 implies 3. We already saw that sigma x I in I x ei ei is orthogonal to ej for all j in I, implies this is implies x equals sigma I in I x ei because that has to be 0 and therefore it implies. Four, 3 implies 4. So we set E to be numbering, so E1, En is numbering of Ei such that xei is not 0. And you take yn to be equal to sigma I equals 1 to n x ei ei. Okay, then yn converges to y in h. Okay, so that is which is equal to sigma I in I x ei. That's how we define this sum. So norm yn square, if you take, so that is nothing but there are no cross terms because ei ej when I is not j is 0. So this is sigma I equals 1 to n mod x ei square. So now let n tend to infinity and we get 4. Okay, so this proves the Parseval's identity. 4 implies 1. So if ei I in I not maximal, there exists a E not equal to 0, norm E equal to 1 and E orthogonal to Ej, Ei for all I in I. Okay, so that is the contradiction of the maximality. But then by Parseval implies 1 which is norm E square equal to sigma I in I mod E ei square, and that is 0 and that's a contradiction. Okay, so this proves the theorem completely. Okay. Corollary, H Hilbert and ei I in I an orthonormal set. Then it is complete if and only if the span of the EIs, that is the subspace generated by finite linear combinations of the EI, that is span of the EI I in I is dense in H. So proof. So if EI is complete, then clearly you take a numbering. So let us say E equal to E1, En, etc. Okay, this is a numbering of all EI such that XEI is not 0. So let X belong to H. Okay. And then we know that X is the limit as n tends to infinity, sigma I equals 1 to n X EI EI, and therefore implies span EI I in I is dense in H. Every element can be approximated from as a finite linear combination of these things. Conversely, so EI, so span of EI I in I dense in H. So if X is orthogonal to the span, this implies X is 0. Now if X is orthogonal to EI for all I, then automatically X is orthogonal to span of the EI, and therefore X equal to 0, and therefore by 1 of by 2, I think by 2, let us see which one it is. Yeah, two of preceding theorem, we have EI is complete. And therefore this is true. Okay. One more corollary. It comes from many things. Okay, so let En n equals 1 to infinity be an orthonormal sequence in H. H is a Hilbert space. Then En weakly converges to 0. Okay, proof. So if X belongs to H, then we have sigma n equals 1 to infinity mod X n square is less than or equal to norm X square. This is the Bessel's inequality. Therefore, this is a convergent series. This implies that Xen tends to 0 as n tends to infinity. Now, every continuous linear functional by Rees representation theorem comes as an inner product with respect to X, and therefore this simply implies that En goes weakly to 0. Okay, so this is an another example, okay, because you have norm En minus Em is always root 2 if you have an orthonormal thing. So no norm convergent subsequence. but this sequence converges weakly to 0, and therefore the weak and norm convergences are strictly different in the case of infinite dimensional Hilbert space. Okay, so we will continue with this.